Hello, my name is Jessica, and the title of the project that I have been working on is Segmented Ultralight Morphing Rotor Wind Turbine Analysis. This is a multi-institutional project consisting of members from 4 universities, the National Renewable Energy Lab, and GE. This project uses a 2-bladed 40-meter diameter scale demonstrator turbine from the 13-megawatt design. This portion of the project is to validate simulation results put forth in a previously published paper by performing data analysis on collected field data. It looks at the blade root bending moment between field and simulation results. There are 6 design load cases that were simulated and are now being validated with the field data. The data analysis began by pre-processing data in MATLAB so that it was in a format that could easily be used and analyzed. Specific parameters were then investigated to match the datasets to the design load cases. Some of these parameters included wind speeds, turbulence intensity, which is a standard deviation of wind speed divided by the mean wind speed, binary bits corresponding to a stop, either normal or emergency, generator power, blade pitch, and low speed shaft position. We found that many data files, over 200 of them, had to be disregarded for blade 2 blade root bending moments due to a faulty sensor in the blade 2 edge bending moment channel. The first 2 DLCs that were investigated had high wind speeds, and one was parked with the rotor idling and the other parked with the rotor locked. For the rotor locked case, all blade 2 root bending moment data had to be discarded because of the faulty sensor. The loads observed for these 2 cases are lower than the loads in the simulation, which could be caused by the lower wind speeds observed in the field data. The simulation wind speeds averaged higher than the field wind speeds, with the highest wind speed observed in the field was around 25 meters per second, whereas the highest simulation wind speed was around 28.57 meters per second. The location of the turbine is a high turbulence intensity site, with turbulence intensities often above the typical 15% value. The yaw error distribution observed with the field data is also lower than the simulation. This lower yaw error leads to lower loads since the turbine blades are more aligned with the wind. The next DLC that was investigated had to do with an emergency shutdown of the turbine. These cases were found by finding non-zero binary bits in the 2 data channels corresponding to normal and emergency stops. Once again, data files had to be removed from blade 2 for the faulty sensor. 3 different causes there were 3 different causes for the normal stops: yaw position error, torque overload, and generator overspeed. The blade root bending moment field data for the normal stops is slightly lower than the simulation data, but still matches the simulation pretty well. For the emergency stop cases, there were 2 causes of the stops: pitch rate not matching what is commanded, and blades offline when they should be on. The blade root bending moment field data for the emergency stops most closely matches the simulation data, with the field data still being slightly lower than the simulation, but well within the expected range. The last DLCs to investigate all had to do with the data collected while the turbine was actually operational. This is where most of the data falls, with over 1,500 files. Operational data was sorted by low and high turbulence intensity, since this location does experience higher turbulence intensity than normal. This site did not experience any of the extreme wind conditions corresponding to DLCs 1.3 and 1.4, so the field data most closely aligns with DLC 1.1, whose simulation results are not shown in the poster. For both the low and high turbulence intensities, the blade root bending moment loads are lower than the loads for DLCs 1.3 and 1.4, again due to the lack of extreme wind conditions. The wind speeds for the operational cases were consistent with the ones used in the simulation, with more variation in the field data than in the simulation. Simulation wind speeds range from around 2 meters per second to 11 meters per second, and the field wind speeds range from 0 meters per second to 30 meters per second, but with the distribution mostly in the lower ranges. Overall, the goal of validating field results against the simulation was largely achieved. There were over 1,700 files that were found to at least partially align with parked or idling, emergency and normal stop, and operational cases. Not all the conditions were matched, leading to the discrepancies that were observed. This is mostly due to different input conditions to the simulation versus the field, and different wind conditions in both. Sensor failure on blade 2 also further complicated the analysis. In the future, the simulation could be updated to more thoroughly encompass the actual conditions that the turbine experiences. Thank you.